Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know, when we usually talk about the search for life in the universe, we have this mental checklist. It's almost like a recipe for biology.
Right, the standard astrobiology checklist.
Exactly. We look for liquid water. We look for a source of energy like the sun or maybe a hot planetary core. And we look for time for things to actually evolve.
And for the last 20 or 30 years, the moons of Jupiter, specifically Europa, Ganymede, and Callisto, have been ticking those boxes one by one.
They really have.
We've confirmed the subsurface oceans. We're pretty confident about the energy sources, mainly tidal heating. They are prime real estate in the astrobiology market.
Prime real estate, yeah. But there's always been this one nagging question mark, a gap in the resume, so to speak, and that is the chemistry. Specifically, the carbon.
The actual stuff that life is built from.
Right, the building blocks.
Yeah.
Because you can have all the warm water in the universe, and you can let it sit there for 4 billion years, but if it's just distilled water, you're not getting bacteria. You're just getting a really excellent bath.
That is a very accurate, if slightly unscientific way to put it. Biology is, at its core, complex carbon chemistry.
It's not just water.
No, it's not. And for a long time, the prevailing assumption in planetary science was that these moons formed as these pristine, almost sterile balls of ice.
Just pure water and rock.
Just water and rock, frozen solid. And if you wanted the good stuff, the amino acids, the complex organic molecules, you essentially had to wait for a delivery.
Like a cosmic delivery truck.
Exactly. You had to hope a comet or a carbon-rich asteroid would crash into the moon later on and deposit those ingredients on the surface.
Which is a bit of a depressing thought, isn't it? I mean, it makes life feel accidental.
It makes it precarious, certainly.
Yeah, like you built the house, but you have to wait for Amazon to deliver the furniture, and the driver might get completely lost.
It relies on chance. But the research we are doing a deep dive into today completely flips that narrative on its head. It suggests the furniture was built into the house from day one.
I love that. So today we're exploring a really groundbreaking set of papers. This is collaborative research from the Southwest Research Institute, Aix-Marseille University in France, and the Institute for Advanced Studies.
Right. They published 2 complementary studies, one in the Planetary Science Journal and another in the monthly notices of the Royal Astronomical Society.
These are major publications, and their core thesis is pretty revolutionary.
It is.
They are arguing that Europa, Ganymede, Callisto, and even Io were not formed as clean, white snowballs. They argue that these moons likely accreted, meaning they gathered up significant inventories of life-building organic materials right from the start.
Right, as they were forming.
And these materials came from both the massive cloud that formed the sun and from the local disk of gas and dust spinning around Jupiter itself.
So no waiting for a comet. The ingredients were baked in.
Baked in and frozen in.
Exactly.
Before we get into the how and the how, involves some incredibly cool simulation work that we're going to break down. Let's define what we are actually talking about here.
Good idea. We keep saying organics or ingredients, but I'm guessing we aren't talking about, sandwich meat floating in space.
No, definitely not sandwich meat, though that would make space exploration much more appetizing. We are talking about COMS. That stands for Complex Organic Molecules.
COMS. Which sounds a bit like corporate jargon, but in astrobiology, that's a very specific term, right?
It is a very specific designation. Now, complex is a relative term here.
Oh, so?
Well, in a high school biology class, complex might mean a protein with thousands of atoms, a massive structure. But in the context of deep space chemistry, the bar is quite a bit lower. We generally define a COM as a carbon-based molecule that has at least 6 atoms.
6 atoms, that's the threshold.
That is the magic number. But crucially, it's not just carbon. It's carbon integrated with oxygen, nitrogen, and hydrogen.
So we aren't just talking about methane, which is CH4, that's too simple?
Right, methane is simple. We're talking about things like methanol or dimethyl ether. These are molecules that act as the structural precursors, the Lego bricks, if you will, for amino acids and nucleotides. So if life is the castle, the COMS are the individual plastic bricks.
Precisely. You cannot build the castle without them. They form the essential foundation for anything that could eventually become biological.
Okay, so where did these Lego bricks actually come from? Because space is Well, it's space, it's a vacuum, it's freezing cold, it's bombarded by radiation.
It's a hostile environment.
Yeah, it doesn't seem like a great place to do delicate chemistry.
Yeah.
I usually think of chemistry happening in a beaker with a Bunsen burner, not in the empty void.
You're entirely right. Space is a terrible place to do chemistry, at least in the gas phase.
Because things are too spread out.
Exactly. If you have two atoms floating in a vast vacuum, the odds of them bumping into each other and deciding to stick together to form a complex bond are astronomically low. Nature needs a workspace, a workbench.
And that workbench is dust.
Icy grains, tiny microscopic particles. Think of them like dust bunnies, but made of silicates rock and coated in incredibly thin layers of ice.
Okay, so little frosted rocks.
Right. And in the early solar system, these grains are everywhere. They're the fog that fills the protoplanetary system. And the ice on them isn't just pure water ice.
It's dirty ice.
Very dirty ice. It contains volatiles, things like carbon monoxide, carbon dioxide, and ammonia, all frozen together on the surface of this tiny rock.
So you have a microscopic rock. It's coated in this dirty ice mixture containing carbon and nitrogen. It's floating in the dark. How does that turn into the precursor for an amino acid?
It needs a spark.
Because otherwise it would just sit there frozen forever, right?
It would. It needs energy. You need a catalyst to get those atoms moving and rearranging themselves into new structures. The research identifies two primary external stimuli that drive this synthesis in space.
And the first one is?
Ultraviolet radiation.
Yeah.
UV photons.
From the young sun.
From the sun, yes, but also from the interstellar environment in general. The galaxy is full of UV radiation from massive young stars.
So the whole nebula is bathed in it.
Exactly. And when a high-energy UV photon hits that icy grain, it acts like a microscopic wrecking ball. It smashes into the simple molecule, say a molecule of methanol frozen on the surface, and it breaks the chemical bonds holding it together.
It snaps the Legos apart.
It snaps them apart.
And it creates what we call radicals in chemistry.
Radicals. I've heard of free radicals in health and diet discussions, usually things we are told to avoid eating. But in space, what are they?
They are essentially unhappy molecules or highly anxious molecules.
Unhappy molecules, I like that.
Chemically speaking, they are fragments of molecules that have unpaired electrons. Because they have an unpaired electron, they are highly aggressive. They want to bond with anything immediately to stabilize themselves.
Okay, so you have this ice grain, the UV light hits it, breaks a bunch of bonds, and suddenly you have this swarm of highly reactive radicals trapped in the ice matrix.
And since they're trapped in the ice, they can't just fly away. They grab the nearest partner.
And when they grab a partner, they build something new. Right. When they recombine, they rarely go back to being the simple molecule they were before. They form larger, weird chains. They form more complex structures. You smash two small things, and the pieces reassemble into one bigger thing. That is the first mechanism for COM formation.
Okay, so UV light is the wrecking ball. What is the second mechanism?
Thermal processing. Heat. But very specifically, not too much heat. This is a classic Goldilocks situation.
Because if it's too hot, the ice just evaporates, right?
Exactly. If the temperature rises too much, the ice sublimates into gas, the radicals fly away into the vacuum, and the chemistry stops. Nothing happens.
But if it's too cold?
If it's too cold, the radicals are frozen strictly in place and can't reach each other to bond. But if you warm it up just enough, the ice lattice, the crystal structure of the ice, loosens up.
It gets kind of slushy.
At a molecular level, yes. It acts a bit like a highly viscous liquid. The molecules can wiggle around. That allows those trapped radicals to migrate slowly through the ice and find each other to react.
So you need a kitchen that is irradiated by UV and slightly warm, but definitely not an oven.
Perfect analogy. And the study points out that a protoplanetary disk, which is the swirling disk of gas and dust around a newborn star, is basically a giant factory perfectly designed to create exactly these conditions.
Because it's turbulent.
Highly turbulent. Grains are constantly moving from cold, dark areas of the disk into warmer, brighter areas, and then getting swept back out again.
Okay, so we have the mechanism, we know how to make the molecules, we have the factory floor, which is the disk. But the big mystery has always been, how do they actually get to Jupiter's moons?
Right, because Jupiter is really far out from the sun.
It's far out, it's cold. And the early solar system was a chaotic mess. Just because you make a complex molecule out by Neptune doesn't mean it gently lands on Europa.
Transport is the killer variable here. And this is where the study's methodology gets really impressive. They didn't just guess at how the transport happened. They built a digital time machine.
A computational model.
Yes. But it's important to understand this wasn't just one simple simulation. It was a complex coupling of two massive physical models that traditionally don't even talk to each other in planetary science.
What do you mean they don't talk to each other?
Well, usually in astrophysics, you have research groups who model the protosolar nebula. That's the huge, massive disk of gas and dust that formed the sun and the entire planetary system.
The macro scale.
Right, the grand scale. And then, completely separately, you have researchers who model the circumplanetary disk. That is the localized, much smaller subdisk spinning around Jupiter, where the gas giant and its specific moons formed.
So it's like a disk within a disk, a small gear inside a massive machine.
Exactly. And the physics work very differently at those different scales. It is notoriously difficult to simulate both at the exact same time. It's akin to trying to simulate the global weather patterns of the Earth and the specific airflow in your living room in the same computer program.
That sounds computationally expensive.
Incredibly so. But these researchers managed to do it. They modeled the evolution of the massive protosolar nebula and the local Jovian circumplanetary disk, and then they mathematically linked them together.
Okay, so they have the wind currents, basically.
Yeah.
How did they track the actual chemistry? Did they just look at the average temperature of the whole system?
No, they went much more granular than that. They utilized a particle transport module. They essentially released thousands upon thousands of digital dust grains into this massive simulation and tracked their individual lives over millions of years.
Like putting tiny GPS trackers on individual specks of dust.
Precisely. They tracked every single time a specific grain moved up or down in the disk, every time it drifted inward toward the sun, every single photon of UV radiation it absorbed, and every fractional degree of temperature change it experienced.
That is incredible fidelity. So they can say grain number 4072 started in the deep outer solar system, drifted inward for 1 million years, got blasted by UV light, and then got sucked into Jupiter's orbit.
They can track exactly that life cycle. And by summing up that incredibly detailed history for millions of particles, they could calculate precisely how much organic material was being cooked up and exactly where it was ending up within the Jovian system.
They integrated the physics of the disk evolution with the transport data to quantify the environmental history of the entire grain population.
Exactly. It removes a lot of the guesswork.
And did they validate this against actual physical data? Or is it purely a math exercise?
No, validation is crucial here. Dr. Olivier Moses from CISOR-RI made a very specific point of this. They compared their model outputs with physical laboratory experiments.
How did you do that?
They essentially asked, if our computer model says a grain gets exactly this much UV radiation and this much heat over time, does the physical laboratory show that those specific conditions actually produce complex organics?
And the answer was yes.
The answer was a definitive yes. The simulation confirms that the dynamic physical environment of the early solar system was highly conducive to the synthesis of these specific molecules.
Okay, so this methodological framework, the time machine, leads us to the study's central finding regarding the origins of Jovian organics. And this is what they call the dual source model.
Yes, the dual source model. This is the absolute headline of the paper. They found that the organic material on moons like Europa and Ganymede did not originate from a single solitary location.
It came from two distinct reservoirs.
Right. Source A and Source B.
Let's break those down sequentially.
Right.
Source A is the protosolar nebula, the big main solar disk.
Correct. The simulation demonstrated that a massive amount of organic synthesis happened way out in the general solar system long before the material ever got anywhere near Jupiter.
Just out in the deep freeze.
Right. The icy grains were drifting slowly through the outer regions, getting hammered by background interstellar UV radiation. They were literally accumulating COMs just by floating there over millions of years.
But wait, I thought Jupiter creates a gap. When a giant planet forms, doesn't its massive gravity clear its orbit? Like a snowplow clearing a street.
It absolutely does. And for a long time, planetary scientists assumed that gap was a hard barrier, that it would effectively cut off the supply line of material from the outer solar system.
Like a moat around a castle. If Jupiter clears the gap, how does fresh, organic-rich dust from the outside get in?
It is a moat, but the advanced hydrodynamic simulations in this study show that the moat is surprisingly leaky.
Leaky.
Yes. The gas and dust don't just stop, the pressure builds up, and the material actually spills over the edges of the gap. It flows across the gap at higher altitudes and spirals rapidly down into Jupiter's personal circumplanetary disk.
So the cosmic delivery trucks can actually cross the bridge.
They can cross the bridge. But the real variable was survival. You are taking a very cold ice grain from deep space and dropping it into the highly chaotic, dynamic, and shockingly hot environment of a forming gas giant.
That sounds like a violent transition.
It is extremely violent. You have massive shock waves, intense frictional heating. You would intuitively think the sudden heat would just destroy the delicate organic molecules.
Vaporize them entirely. Sterilize the package before it even arrives at the moon.
Exactly. But the model showed something counterintuitive. It showed that nearly half, 50% of the particles actually survived the trip.
Half of them.
Yes. They managed to stay just cold enough during the transition. They successfully transferred their entire cargo of comms from the larger solar nebula down into Jupiter's disk without undergoing major chemical alteration or thermal destruction.
That is a surprisingly high survival rate. So half the organic material on the Galilean moons is basically imported from the rest of the solar system.
Correct. That ancient interstellar heritage is source A. But then there is source B, the Jovian circumplanetary disk itself.
The local neighborhood.
Right. The research found that Jupiter wasn't just passively collecting material from the outside. It was functioning as its own chemical factory.
It was making its own organics locally.
Yes. The circumplanetary disk, that swirling nursery directly around Jupiter, had its own localized Goldilocks zones. If you think about the physics happening there, you have massive amounts of gas swirling incredibly fast into Jupiter's gravity well.
And that creates friction.
Massive friction, like rubbing your hands together vigorously on a cold day, but on a planetary scale. This creates what physicists call viscous heating.
Viscous heating?
Yes. This viscous heating raised the ambient temperature in certain specific regions of Jupiter's disk just enough to trigger that exact thermal processing we talked about earlier.
The slushy ice.
Exactly. So even if the material crossing the gap from the outside was completely dead and sterile, Jupiter's local disk environment would have cooked that raw material into complex organics anyway.
This is a redundancy mentioned in the research. It's a built-in failsafe.
It is a brilliant natural failsafe. It means you don't need to be exceptionally lucky to get organics. If the solar nebula source fails, say, the interstellar radiation wasn't strong enough, the local viscous heating source kicks in and does the job.
And if the local source is too weak, the solar nebula source covers the shortfall.
Exactly. The convergence of these two distinct mechanisms implies that having organic-rich moons isn't some rare anomalous fluke. It is a highly robust feature of the system.
It's an inevitable outcome of the physics. If you build a gas giant, you are almost guaranteed to build organic-rich moons around it.
The presence of comms is essentially a structural guarantee.
That is huge. I want to pause on that for a second. Because we always talk about the habitable zone in astrobiology strictly in terms of distance from a host star. We say Earth is in the zone, Mars is on the edge, Venus is too close.
The traditional liquid water zone.
Right. But this research suggests that gas giants carry their own portable habitable chemistry sets with them, regardless of where they are.
That is a phenomenal way to put it, a portable chemistry set. The disk itself provides the necessary gradients of heat and radiation.
So let's talk about the final customers in this process, the Galilean moons themselves, Europa, Ganymede, Callisto, and Io. They were sitting there in this disk, growing, sweeping up all this material.
They grow through a process called pebble accretion. That is the current, most accepted model in planetary science.
Pebble accretion?
Yes. They aren't just getting randomly hit by massive asteroids to grow. They are constantly sweeping up these centimeter-sized pebbles of ice and dust as they orbit through the disk.
Like a vacuum cleaner.
Very much like that. And thanks to this dual-source modeling, we now know with high confidence that those pebbles were heavily loaded with comms.
So when Europa initially formed, it wasn't a pristine white ball of ice that slowly got dirty over billions of years of comet impacts. It was what? A dirty snowball right from the start.
It would have been a profoundly muddy, organic-rich slurry, a dark mix of silicate rock, water ice, and this complex organic tar, all mixed together from day one.
And this directly challenges the older pristine hypothesis.
It completely dismantles it. The pristine hypothesis assumed the foundational water was pure H2O. But if this new model is accurate, these moons were chemically complex from their very inception.
And that matters tremendously because of what happens next in a moon's life cycle. Differentiation.
Yes, the crucial stage of internal differentiation.
That's when the moon gets hot and separates into layers.
Right.
The heavy stuff sinks to the metal, The light stuff floats to the top.
Right. As these large moons grew, the immense pressure of their own gravity, combined with heat from radioactive decay inside the rocks, caused them to warm up internally. The vast quantities of ice melted.
Creating the subsurface oceans.
Exactly. The heavy rocks sank to form a dense core, and the liquid water formed the massive global mantle and the icy crust on top. Now think about the organics. If the organics were just painted onto the surface much later by random comets, they would just sit on top of the frozen crust.
They might never actually reach the liquid ocean deep below.
They might remain isolated forever, but if they were built directly into the structure of the moon during pebble accretion...
Then, as the moon melted and differentiated, those organics were churned right into the liquid mix.
Exactly. They would be in direct contact with the liquid water immediately. They would be subjected to intense hydrothermal processing deep inside the moon at the boundary between the rocky core and the ocean.
This brings us to the S word, soup.
Primordial soup, yes.
Because that is really the fundamental question we are asking, isn't it? Are the subsurface oceans of Europa and Ganymede just sterile saltwater? Or are they a complex chemical broth?
This specific study strongly suggests it is a broth. And not just any broth, a highly potent prebiotic broth.
Break that down for me. What actually happens chemically when you take these space-made comms, which remember are just the precursors, and you soak them in warm, pressurized liquid water for 4 billion years?
You get a process called hydrolysis. You get extensive aqueous alteration. The specific molecular structures we see forming in the space environment, things like hexamethylnitramine or HMT or various complex organic polymers, when you subject them to liquid water, they break down into very, very interesting secondary structures.
Like what?
They transform into amino acids. They transform into the nucleobases required for nucleotides.
The actual literal stuff of DNA and RNA.
The foundational components of life as we understand it. In astrobiology, we constantly discuss the bottlenecks for life, the immense hurdles that stop life from initiating.
Usually we think the biggest bottleneck is just getting the raw materials in the same place. Do we have enough reactive nitrogen? Do we have enough reduced carbon?
Exactly. And this paper effectively states, yes. The delivery truck arrived, it emptied an immense cargo of the right materials, and the planetary environment cooked it.
The study implies that the chemical barrier to habitability is effectively removed for these worlds.
If you have a moon forming around a gas giant, you inherently have the foundational ingredients. Consequently, the variables required for habitability narrow down significantly. It is no longer a question of do we have the chemical bricks. It becomes do we have the sustained energy and the solvent stability to build something with them.
And we know there is energy. We know Europa has tidal heating flexing its core.
We know the energy is there. So suddenly the mathematical equation for life on a world like Europa looks much, much more favorable than it did under the pristine ice models.
I want to shift gears and talk about the odd one out in this Galilean family.
Poor Io.
Io is an absolute hellscape. It's covered in active volcanoes, sulfur flows, lakes of lava. There is no water ice to be found, but it formed in the exact same disk right alongside Europa.
It did. And the transport model shows conclusively that Io accreted the exact same organic-rich pebbles as Europa and Ganymede. It started with the exact same astrobiological starter kit.
So what on earth happened to it?
It simply got too close to the boss. Io orbits so close to Jupiter that the gravitational tidal forces are absolutely immense. The physical friction generated deep inside Io literally melts solid rock.
It drove off all the water.
It boiled away all the water into space. It drove off all the volatile elements. And it undoubtedly pyrolyzed, meaning it essentially burned to a crisp all of those complex organics billions of years ago.
So Io is what happens when you leave the prebiotic cake in the oven at 5,000 degrees.
That is exactly what it is. A charred remain. The rich organic material that Io initially accreted would have been aggressively broken down into much simpler carbon and sulfur compounds. This contributes heavily to Io's current bizarre, exotic surface chemistry, but it completely destroyed any potential for biology.
It really demonstrates that accretion is only the first chapter of the story. The subsequent geological evolution determines the ultimate fate of those delivered organics.
Exactly. Delivery is necessary, but not sufficient.
And then, on the other extreme, there is Callisto, the quiet sibling.
Callisto is scientifically fascinating precisely because it is the control group in this grand experiment. It orbits much further out from Jupiter. Because of that distance, it experiences very little tidal heating.
So it didn't fully differentiate like Europa did.
Right. It is often described by planetary geologists as a dirty ice ball that never truly separated completely into a distinct rocky core and a pure water ocean. It's more mixed.
So if we eventually send a lander to Callisto,
We might actually find the pristine fossils of this entire accretion process. The original palms might still be locked within the ice matrix, completely untouched, exactly as they were delivered 4.5 billion years ago.
while Europa has been actively processing and recycling its organics in a warm ocean, Callisto might just be storing them in a deep, dark freeze.
It is a profound cryogenic time capsule. That is a highly compelling reason to visit Callisto.
And speaking of visits, we aren't just theorizing about these moons on whiteboards anymore. We have major hardware currently on the way.
We absolutely do. We are entering the golden age of Jovian exploration.
NASA's Europa Clipper mission is en route, and the European Space Agency's JUICE mission.
JUICE stands for Jupiter Icy Moons Explorer.
Right. Both of these billion-dollar spacecraft are flying there now. Based strictly on the findings of this study, what are their instruments actually looking for? If you were the lead scientist sitting at the console when the telemetry starts flowing in, what specific data point tells you, aha, the dual source model was correct?
It ultimately comes down to isotopic ratios.
Explain the isotopes.
Isotopes are essentially chemical fingerprints. They tell you where a molecule was born. Specifically, the instruments will look at the ratio of deuterium to hydrogen.
Deuterium being heavy hydrogen.
Yes. Deuterium is an isotope of hydrogen that possesses an extra neutron, making it twice as heavy. Now, the physics of chemical reactions dictate that in the incredibly cold, dark reaches of the interstellar medium and the far outer solar nebula, reactions tend to strongly favor incorporating deuterium over normal hydrogen.
Because the cold temperatures affect the reaction rates.
Yes, it relates to the zero-point energy differences in the chemical bonds. The result is that water and organics formed in the deep cold are highly deuterium-rich. They have a very specific, elevated signature.
Okay, and the material formed in the warmer local Jovian disk via viscous heating.
That material formed at higher temperatures. Therefore, it would incorporate much less deuterium. Its isotopic ratio would look much more like the standard baseline solar value.
So the Europa Clipper has sophisticated instruments, like mass specs, the massive mass spectrometer that can literally taste the dust flying off the moon's surface.
MassPex is an incredibly sensitive piece of hardware. It can sniff the extremely tenuous gas plumes or analyze the microscopic dust kicked up by micrometeorite impacts on the ice.
And if it detects these complex organics in that dust, the very first thing the science team will do is check that deuterium to hydrogen ratio.
Exactly.
And if the ratio is very high.
A high ratio directly points to source A. It confirms the material originated in the distant solar nebula and possesses that ancient interstellar heritage.
But if the ratio is mixed,
If they find a mixed isotopic signature, it serves as direct observational confirmation of the dual source model. It physically confirms that Europa is a hybrid world built from both distant and local material.
that is essentially molecular archaeology, reconstructing the history of the solar system by sniffing gas puffs from a moon 400 million miles away.
It really is. And Dr. Mouses strongly emphasizes that connecting this laboratory chemistry and the disk physics is absolutely essential for interpreting the measurements these spacecraft will send back. The theory provides the critical framework for the data.
And the ESA JUICE mission is focusing heavily on Ganymede, right?
Yes, Ganymede is its primary target, and Ganymede is the absolute giant of the system. It is the largest moon in the entire solar system. It is physically larger than the planet Mercury.
It even has its own magnetic field.
It does, and structurally, it possesses a very deep, massive, multi-layered subsurface ocean. Because of its sheer size and gravitational pull during formation, the raw volume of pebble material Ganymede swept up is staggering.
So if this dual source model holds true, the sheer tonnage of complex carbon stored inside Ganymede is mind-boggling.
It would act as a planetary-scale organic storage tank.
With a global ocean sitting right underneath it waiting to mix.
Exactly. The astrobiological potential is immense.
I want to step back a bit and look at the larger why should I care aspect of this research. We have established that Jupiter's moons are highly likely to be rich in the complex building blocks of life. We have established a robust physical mechanism that explains exactly how it happened. But this paper goes a step further in its implications. It talks about the universality of these processes.
Yes. This is perhaps the most important takeaway. This isn't strictly a story about Jupiter. It is a fundamental story about how gas giants operate everywhere.
Because physics is physics, right? Fluid dynamics and gravity work the exact same way in the Andromeda Galaxy as they do right here in our solar system.
Precisely. The specific processes the researchers modeled, the viscous heating of the gas, the ultraviolet irradiation of the grains, the mechanics of pebble accretion, the hydrodynamic flow across the gap, these are universal physical laws.
So every time a gas giant forms around any star, it should behave similarly.
Every single time a gas giant forms, it generates a circumplanetary disk. It clears a gap in its local nebula. It naturally creates these precise thermal and radiation zones.
And if we look at the current exoplanet data, our telescopes have found thousands of gas giants out there.
Thousands of them. We call them Jovians or super Jovians, and a significant percentage of them are located in the habitable zones of their respective host stars or even further out in the colder regions.
If this accretion mechanism is truly universal, then every single one of those thousands of gas giants likely possesses a system of moons.
And those moons, dictated by this exact physics, should be heavily loaded with complex organics from the moment they coalesce.
It implies that the universe is essentially functioning as a massive automated factory for manufacturing habitable moons.
It suggests a paradigm shift. It suggests that the chemical habitable zone isn't restricted to a narrow band around a star. The chemical habitable zone is effectively the entire galaxy. We used to rigidly think you had to be in a very specific, lucky spot to get the chemistry right.
Just the right distance, just the right planet size.
But this study says no. The formation disk itself manufactures the necessary chemistry and actively transports it to the growing planetary bodies.
That is a profound philosophical shift. It moves the concept of life from being a lucky, highly contingent accident of location to being an almost inevitable consequence of standard planetary formation.
It strongly indicates that the fundamental ingredients for life are standard equipment for planetary systems, rather than premium upgrades.
But of course, having the ingredients in the bowl isn't the same as having a baked cake.
Absolutely not. You still require the spark. You still require long-term environmental stability. We have not found life yet. But what this research does is force us to stop making excuses about the chemistry.
We can't say, oh, maybe there's just no carbon out there in the dark.
Right. The carbon is there, the nitrogen is there, the liquid water is there, the energy is there.
The table is fully set.
The table is set. Now the scientific community just has to send the probes to see if anything actually showed up for dinner.
And that is exactly what Clipper and Juice are going to tell us in the coming decade.
Fingers crossed, the data return will be historic.
One specific detail in the paper I found really mechanically interesting was the nitrogen issue. You mentioned nitrogen earlier as a key component. Why is that specific element so notoriously tricky to model?
Nitrogen is highly volatile. In the raw environment of the solar nebula, it strongly prefers to exist as N2 gas. Molecular nitrogen.
Like our atmosphere on Earth.
Exactly. And the physical problem is that it is exceptionally hard to build a solid planet or moon out of a gas. It doesn't stick to the grains. It doesn't freeze onto the ice until the ambient temperature drops incredibly low, significantly colder than the orbit of Pluto.
So how do you possibly get enough solid nitrogen into a forming rock and ice moon like Europa?
That has been a major theoretical puzzle. If Europa just accreted pure water ice and silicate dust, it would be severely nitrogen poor. And biology absolutely requires nitrogen. Amino acids are literally amines. They're built around nitrogen groups. DNA utilizes nitrogenous bases. No nitrogen, simply no life.
So how did the dual-source COM model solve this missing nitrogen problem?
The study details how the synthesis of COMs actively traps the volatile nitrogen. The chemical reactions form things like complex ammonia salts or organic amines that remain in a solid state at much higher temperatures than N2 gas.
So the complex organic chemistry acts like a molecular trap. It grabs the slippery nitrogen gas out of the nebula and locks it securely into a solid, heavy molecule.
That is the exact mechanism. It chemically sequestered the volatile nitrogen directly into the physical structure of the dust grains. So when the Galilean moons swept up and accreted that dust, they got the critical nitrogen delivered for free.
This solid phase delivery mechanism is critical.
Without the specific mechanism, the moons might be incredibly rich in liquid water and carbon, but lethally nitrogen poor, which would represent a severe, perhaps insurmountable constraint on their biological potential.
The COM accretion model comprehensively explains how the N in CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, physically arrives at the moons.
Yes, it solves a major mass balance issue in the planetary chemistry.
It's incredible how many little physical and chemical things have to go exactly right. But the mathematical model seems to show that they do go right. naturally and reliably.
That is the structural beauty of it. It isn't a fragile Rube Goldberg machine where one tiny slip-up ruins the entire sequence. It is a physically robust, redundant system. The fundamental physics of the universe actively favors the generation of chemical complexity.
I want to circle back to the methodology one last time because Dr. Olivier Mousis from CESWA-RI made a compelling point about connecting the lab to the sky.
Yes. This represents the new gold standard in planetary science methodology. You can't just be a traditional astronomer solely looking through a telescope anymore, and you can't just be a theoretical coder writing pure simulations in a vacuum.
You actually have to get your hands dirty in a physical lab.
You have to execute the empirical chemistry. They literally utilize advanced vacuum chambers in these laboratories, specifically at Aix-Marseille and CESWA-RI, where they meticulously create fake space.
How do they do that?
They physically cool a metallic surface down to 10 Kelvin near absolute zero. They then spray precise ratios of water and methanol vapor onto it to manufacture microscopic layers of ice. And then they blast that synthetic ice with high-powered UV lasers.
Just to see exactly what happens to the molecule.
To empirically measure the reaction rates, they ask, how fast does methanol break down under this exact photon flux? How much specific thermal energy does it actually take to synthesize glycolaldehyde?
And then they take those hard empirical numbers from the physical lab and plug them directly into the computer code.
Exactly. This grounds the simulation and reduces the theoretical uncertainty significantly. We are no longer guessing if the chemistry happens. We mathematically know it happens under those specific physical conditions, and the hydrodynamic model verifies those exact conditions existed in the Jovian disk.
It makes the findings feel much, much more solid. It isn't just we theorize this might happen. It's we observe this happening in the lab, and the computational physics confirm the early solar system matched the lab conditions perfectly.
Precisely. It rigorously bridges the massive gap between the microscopic realm, individual atoms reacting on an ice surface, and the macroscopic realm, giant planets forming in a stellar disk.
The particle transport module in the paper also specifically highlighted radial migration and vertical migration. Can we unpack that fluid dynamics aspect a bit more? Because it sounds like these microscopic grains are undergoing epic journeys.
They absolutely are. The protoplanetary disk is not a static, flat ring. It is a highly turbulent, three-dimensional swirling cloud of gas. Vertical migration means the dust grains are constantly being lofted high up above the dense midplane of the disk and then slowly settling back down due to gravity.
Like dust motes circulating in a drafty room.
Very much so. But this vertical circulation is crucial for the chemistry because the ultraviolet radiation from the young sun cannot physically penetrate deep into the dense, thick midplane of the disk. The midplane is completely dark.
So only the upper surface layers get irradiated by the UV wrecking balls.
Right, so this vertical cycling effectively acts like a massive conveyor belt. It actively brings fresh, simple grains up to the irradiated surface, zaps them with UV photons to generate those reactive radicals, and then cycles them back down deep into the darker, warmer midplane where they can thermally process safely.
So the inherent turbulence of the gas is actually driving the complex chemistry.
It is the essential engine. Without that vertical turbulence, the grains would simply sit in the dark midplane forever and nothing complex would ever synthesize. The dynamic mixing is mandatory.
And what about radial migration?
Radial migration describes the movement inward toward or outward away from the central star. The study relies heavily on the concept of gas drag.
Friction with the nebula.
Exactly.
Yeah.
As these solid grains orbit, they constantly feel the aerodynamic friction of the surrounding gas. This drag slowly robs them of orbital momentum, causing them to gradually spiral inward toward the center.
Toward Jupiter's feeding zone.
Toward the sun initially, and eventually directly into the gravitational feeding zone of the forming Jupiter. Now, the speed of this inward migration depends heavily on the physical size of the grain.
Which is why they focus on specific sizes.
Right. The study specifically focuses on grains in the micrometer to millimeter size range.
The pebbles.
Pebbles. These precise sizes possess the exact aerodynamic properties to be most susceptible to gas drag. If the dust grains are too small, they remain perfectly coupled to the gas and just float along with it indefinitely. If they are too massive, like a boulder, they simply plow through the gas unaffected.
But these specific millimeter pebbles hit the aerodynamic sweet spot. They drift perfectly into the planetary accretion zones.
The hydrodynamic simulations clearly show that these pebbles are the primary hyper-efficient vectors for delivering the bulk comms to the growing moons.
It is truly amazing to think that the profound building blocks of biology are basically delivered by cosmic gravel.
It is humbling, and the sheer physical volume of that gravel is astounding. We aren't talking about a light sprinkling of organics. We are talking about multiple Earth masses worth of complex carbon being chemically processed and physically moved around the Jovian system.
So looking forward to the future of this field, we have the upcoming spacecraft missions. We have a highly robust theoretical framework. What is the next major theoretical hurdle? If this paper fundamentally solves the delivery problem, what is the next major problem we need a deep dive on?
I would say the absolute next big frontier in astrobiology is the concentration problem.
Concentration.
Yes. You have a massive global ocean. You have trillions of tons of complex organics successfully delivered and dissolved in it. But biology usually requires a high local concentration to actually initiate.
It can't just be infinitely diluted.
Exactly. It needs a tide pool, or a porous hydrothermal vent structure, or perhaps an active ice-water interface at the crust. The chemistry needs to be confined. We need to rigorously understand how these dilute, dissolved organics get concentrated densely enough to begin the processes of self-replication and metabolism.
So we have successfully moved from asking, is there any flour in the kitchen, to asking, how do we properly mix the dough?
That is a perfect summary. We are moving up the hierarchy of biological complexity. But crucially, we couldn't even legitimately ask the concentration question until we comprehensively solved the delivery question.
And this research solves the delivery. Now, we know for a fact the global ocean is a viable chemical feedstock. Now we can start accurately modeling the hydrothermal vents.
It is an incredibly exciting time to be following planetary science. We are literally rewriting the fundamental history of our own solar system in real time.
And potentially rewriting the history of every solar system in the galaxy.
Absolutely. The implications are universal.
So, to comprehensively wrap this up for you listening, we started this deep dive with a traditional view of the Galilean moons as purely icy, potentially habitable in terms of water, but chemically completely mysterious worlds.
And through the lens of this research, we have ended with a view of them as massive dynamic chemical factories born from a robust dual lineage of ancient interstellar dust and vigorous local thermal processing.
They are worlds that were essentially pre-programmed for advanced prebiotic chemistry from the moment of their physical accretion.
And that profound chemical complexity isn't a random accident. It is a direct, mathematically predictable consequence of exactly how gas giants form within a protoplanetary disk.
Which strongly means the entire galaxy is highly likely teeming with organic-rich, habitable moons.
The statistics certainly point in that direction.
I will leave you with this final thought. In astrobiology, we spend an enormous amount of time and telescope resources looking for Earth 2.0. We look for rocky planets sitting in the warm, comfortable zone around a yellow star. But perhaps we have been fundamentally biased by our own origins.
We look for what we know.
Exactly. But maybe the actual default mode for life in the universe isn't sitting on the dry surface of a rock near a star. Maybe the default, statistically speaking, is deep under miles of ice, orbiting a massive gas giant, swimming in a rich organic soup that was meticulously cooked up before the planet was even finished building itself.
It is a very real, mathematically supported possibility. The universe is vastly more creative than we give it credit for.
It certainly changes how you look at Jupiter when you see it shining in the night sky. It's not just a big inert ball of gas. It is the hydrodynamic engine that might have sparked biology across a dozen moons.
A very large, highly efficient cosmic mixer.
Thanks for taking this deep dive with us today.
It was my pleasure.